Hey guys, so in this video we are going to work through the handout for lesson 9.3 on the normal distribution. This is an important topic in our course, and of course we'll review it when I'm back, but it is very important that you guys work through this and try your very, very best to understand it, fill in the handout, and do the homework questions. We'll skip the warm-up and focus instead on the material at hand. Last day we looked at binomial probability distributions, which was a special case of discrete probability distributions. So today we're moving on from discrete data, and now we are considering continuous random variables. So things that you can measure, which can take on a continuum of values. So for instance, now we could be talking about height, where I could be 160 centimeters, I could be 160.011, kind of any value, not just specific isolated values. It could be weight, distance, things like that. And actually the continuous probability distributions we're going to look at are all going to have this bell-shaped curve. This is called a normal probability distribution, and it is centered around some average, which we will use the Greek letter mu to represent. Now these are asymptotes on the left and right. They actually do go on forever, which may or may not be realistic for your situation, but very little of the data lies kind of in these tail areas, so we just choose to ignore those. So many naturally rising probability distributions follow this shape, and they are symmetrically centered about the mean. If you wanted to graph this equation, you can use this really ugly function here. That is beyond the scope of our course, but in case you're interested, you can take a look. So these normal distributions, they are completely determined by the mean, which is the center, and the standard deviation, which tells you how far spread out. You could have a bell-shaped curve that's very wide, or you could have one that's very narrow, and they could be centered around the same mean. And it's completely, that kind of narrow versus wide is determined by the standard deviation. So both the mean and the standard deviation are extremely important for the normal distributions. Okay, now if you have a data that's normally distributed, you can see from this picture, it's centered about the mean, but 68 roughly percent of the data lies within one standard deviation of the mean in either direction. So if we go here to here, this is one standard deviation in either direction. We find 68% of our data. We get like 95% if we go another standard deviation away. If we go 3, we actually get over 99% of our data. So you can see what I mean, why the tails might go on forever in either direction, but a very, very small amount, for less and less data lies on the curve the further out you go. Now, let's look at some properties of the normal distribution. In a data set that's normally distributed, the mean, median, and mode are all equal. Okay, I've already told you it's centered about the mean. That is the highest point. Remember, we have frequency on the y-axis. So the highest point is the most frequently occurring, the mode, and it's completely symmetric. So because the same amount of data lies to the left of the median as lies to the right, that it means that the median also is the center of the data. We've already talked about this, but 68%, 95%, 99%. And more than a few standard deviations from the mean, values have a very tiny chance of occurring. Now, for our purposes, here's what's really important. If you take an entire normal distribution, the area under the whole curve, including the infinite kind of tails, this total area, which I'm shading in red, equals 1. Okay? Now, if I want to know, say if I have some point little x, the probability that x is less than little x actually corresponds to the area to the left of this point. So this area is the probability, that x is less than little x. So that's kind of interesting. Now, how do we find that area? We'll talk more about that later. But this blank here, left. Now, on the other hand, the probability that x is greater than some little x is the area to the right. So that should say right. And the final case, if we have two little x's, x1, x2, the probability that x lies between x1 and x2 is given by the area between those two values. So this is the probability that x is between x1 and x2, and this was the probability that x was greater than a little x. So finding probabilities for normal distributions is related to finding the area underneath the bell curve that matches the situation you're in. Okay, so let's move on. In terms of notation, if you have a normal distribution with mean mu and a standard deviation sigma, you write it this way. This is shorthand for you have a normal distribution with mean mu and standard deviation sigma. So you write sigma squared, and that's the variance. So, for example, if I had a normal distribution with mean 3 and standard deviation 4, I can represent that this way. Remember, this is the standard deviation squared that we put in there. That's just notation, just so you know if you see n bracket 316, you know what that means. Okay, so we're going to look at an example. Now, to do this example, to actually compute the probabilities, we are going to use our calculators. And I have posted another video showing you what kind of calculator commands to put in. So please watch that, perhaps right after this example, or as you go. You can flip back and forth between them. But I'll show you how to set up the problem to at least get partial marks if you get it wrong. So we're looking at cars passing by a supermarket, and their speeds are normally distributed. Their average speed is 53.6 kilometers per hour, and there's a standard deviation of 7.4. So part A, they say, okay, if I pick a random car, what is the probability the car is going between 60 and 75 kilometers per hour? So I want to calculate this value, and always draw the picture of the normal distribution. So my average is here, 53.6. So to make an accurate picture, the area I want is between 2 points that are both to the right of the average. So I want to calculate this area. That area will give me the probability that x is between 60 and 75. Now, if I put this into my calculator, I'm going to do this on the side here. You guys should know how to do this if you've already seen the other video. It's a menu, probability, distributions, normal CDF between 60 and 75, the mean 53.6, and standard deviation 7.4. And I get that this is actually 0.192 rounded to 3 significant figures. So there's a 19% chance that a car that passes by is going between 60 and 75 kilometers per hour. Now, I will set up the other one. So in part B, you want, okay, it's going at most 70 kilometers per hour. So that means it's going less than or equal to are both exactly the same probabilities for normal distribution, because the probability of having any exact value is actually 0. I can never measure a continuous variable exactly because I'm limited by whatever measuring device I'm using. So for instance, if you ever see an equal sign on a normally distributed data set and you want to find the probability, that's always 0. So less than and less than or equal to are the same. Now I can plug that into my calculator. The picture, okay, so if the average is 53.6, we want everything to the left of 70. And we want this whole area. Doing a kind of a poor job of shading, but that's okay. And if I plug that into my calculator, let me just take a moment to do that. So here, my lower bound is something really negative. I'm going to put in like negative 10 million. Upper bound 70. We get 0.987. And for C, I won't do C just to save some time, but it's the probability that X is greater than 60. So you guys should be able to fill that in. Really quick, before we're done here, you will very commonly, especially in our final lesson next day, see this particular normal distribution mentioned. And that is a normal distribution which has a mean of 0 and a standard deviation of 1. That is called the standard normal distribution. And you'll actually notice your calculator defaults to mean 0, standard deviation 1 when you hit normal CDF. If you see the random variable z being used instead of x, they are referring to a standard normal distribution. So if we want to calculate the probability that z is less than 0.12, okay, we're using z's, so that means our mean is at 0. 0.12 is just to the right. And so we want to find this whole area. And this is just normal CDF with an upper bound of 0.12 and a really big negative lower bound. So I'll put this in the calculator quickly. So negative 7 high, upper bound 0.12, mean 0. Standard deviation 1 is 0.548. And in fact, any normal distribution, we can transform any normal distribution into the standard normal distribution by taking every x value in our data set, subtracting the mean and dividing by the standard deviation. And that will convert it into a corresponding data point that lies in this new normal distribution with mean 0 and standard deviation 1. And before graphing calculators, we actually had to kind of always do this. And because rather than punching our calculator, we would look it up in tables that were calculated about the standard normal distribution. Okay, real quick, we'll just look at this last example before we finish. Okay, so IB1 June exam scores last year were normally distributed with a mean score of 76.1 and a standard deviation of 13. This is a fairly realistic situation. Now, in 1, we want to know what is the probability that a randomly selected student scored at least 80%. So if X is our data, continuous random variable, we want to know what is the probability that X is greater than 80. That in our situation, we are centered at 76.1. Our picture is to the right of 76.1, and we want this blue area under here. Right? Now, that's something we just need to punch into our calculator. Our lower bound is 80. Our upper bound should be infinity, but we need to represent that as some very large number. Average is 76.1. standard deviation 13, and we get 0.382. And finally, let's do number 2. Now, number 2 is a common sort of thinking question that pops up on these sometimes. So we want to know, what is the probability that out of 10 randomly selected students, at most half of them scored 80%? Now, this actually brings us back to binomial probability. What we're doing here is a binomial experiment. We choose a student, either they score more than 80%, which we will call a success, or they score less than 80%, which would be kind of a fail in this situation. We have 10 trials, so this is binomial with 10 trials. Probability of success, P equals 0.382. And we are interested in the probability that X is most half of them, so less than or equal to 5. Note that what they really wanted here is that at most half of them scored at least 80%, so the wording should have been a bit more clear. Okay, so this is something you would enter in your calculator, right, using the binom CDF, right, with a lower bound of 0 and upper bound of 5, P equals 0.382 and 10 trials. And remember, we got this P equals 0.382 from A. That in A, we calculated on any one trial what is the probability a randomly selected student scored at least 80%. So I'm on my calculator now going to put this into binom CDF. Number of trials 10, probability of success 0.382, lower bound 0, upper bound 5. And we get 0.862. And again, on my calculator, what I put in there was trials 10, probability 382, lower bound 0, upper bound 5. So that's kind of a nice question that combines continuous and discrete probability. So that's it. Try the homework I have posted. It is crucial that you try this, and we will take it up next class. Thank you.